Okay, so let me say a little bit more about I don't know if you remember where we were last time. We were discussing. I think we ended the discussion last time with some discussion of the beta function of the phi to the 4 theory. It might have been it's been a couple of weeks, so I'll just recap that. And I want to say something about the RG group. And then the idea is we'll start a discussion of path integrals because you should have some exposure to how the formalism of field theory is done using path integrals. And then I plan to discuss at least scalar QED. I was hoping also to discuss fermionic systems, although it's not clear to me that we will actually manage to do this in the next 4 lectures. You guys did some of it in the tutorials. Okay, so I'm not sure if we'll manage to actually cover it in the lectures itself. Okay. Yeah, we have a bit of a choice between trying to do path integrals and trying to do fermionic systems, and I felt maybe you could see path integrals and gauge fields and QED than trying to see fermions, and which is also important. But I think we're about a couple of lectures short of finishing things. Okay, so yeah, I wanted to say a little bit about how a little bit about the renormalization group, and go back to the discussion of the beta function. And just so this is a pretty brief discussion. You can have much more discussion on this topic, but I want to give you a brief discussion of this. So let me remind you, we studied already renormalization in several theories. And what was our idea, right? For example, in the phi to the 4 theory, we said, we had some Lagrangian. Can you hear? Okay, you can hear me online?
Yes.
Okay, good. Okay, so the discussion we had was, that we had some Lagrangian of this kind, and we found when we did some calculations, we found infinities, and so we said, we'll add to this some term and we'll adjust these terms A, B, and C so that you get finite answers, right? So we'll introduce a cutoff. So we'll add this. We'll introduce a cutoff. Adjust A, B, C. Okay. And we found that the infinities go away. Okay. Now, when people first thought of this, they thought this was a trick, that you introduce some parameters and the infinities vanish. In fact, the way we've introduced it, perhaps it's already been clear that it wasn't quite a trick, but rather, that these parameters we should have thought of as some microscopic parameters of the theory, and not related necessarily to the parameters that we observe. Although, initially when people came to this understanding of renormalization, they just thought this was some trick to make infinities vanish. But as I've tried to emphasize, it's not a trick, and there is some physics here. Okay. However, one could still ask, given what we have, right, when does this procedure work and when does it not work? Right? So you can check, in fact, that let's say I was to add to this another term, and I was to say, and I was to try to add this kind of a counter term, then you would find that this procedure would not work. Okay? It would not work, and and what would happen is you would find that just adding the single counter term would not be enough, but you would need to add more and more counter terms, okay, so as to make these terms, so as to get finite answers. And these kinds of theories are what used to be called non-renormalizable theories. So people worked with various theories, and they found which theories were renormalizable and which theories were not renormalizable. And in general, from this old perspective, it's not quite clear when you should get the answer that you get. Okay? So in this case, maybe you can work it out with phi to the 4 and phi to the 6. You say this is a renormalizable interaction, this is a non-renormalizable interaction. But someone could say, well, what if I wrote down phi to the 7 minus phi to the 24 by 4? right? Is this particular combination renormalizable? Or is there some other combination maybe that I cleverly construct that's renormalizable? You could ask questions of this kind, and it turned out that in the end, the final answers that people found were pretty simple. Okay? And the final answers that people found were that you basically had to look at the dimension of the coupling constant. Okay? And in the case where the dimension was suppressed by a power of the energy, like this, those interactions were not renormalizable. In the case where the dimensions were dimensionless or they came with positive powers of energy, those interactions were renormalizable. Okay? So I want to explain a little bit about how you might think about this from what's called a Wilsonian perspective. Okay? So the basic idea of the Wilsonian perspective, is to say that let's take seriously the idea that we have a cutoff lambda. Okay? So take seriously and then we try and ask, so if we take seriously the idea that there's a cutoff, then there's no infinities. Okay? Now you can write down some Lagrangian which just looks like these are some operators. This is some general form for writing operators of this kind, and by construction in the presence of a cutoff there are no infinities. So now there are no infinities. There are no infinities because you have a cutoff. Right? You put a cutoff. Okay? However, we can ask how these parameters gi change as you flow the cutoff, and that's the subject of the study of the renormalization group. Okay? And that's the question that the renormalization group tends to answer. Okay. Now let's see. What else do I want to say? Yeah. Okay. So some parts of this answer are actually pretty easy to get. Okay. The parts of the answer that are pretty easy to get, some part of this answer is fixed by dimensional analysis. Okay. And that is simply that if you start with some operator, if OI has m phi's and n derivatives, then its dimension delta. So delta I, this is the dim of OI. That's this dimension. This is the operator. This delta is just equal to n plus n. Okay. Therefore, you can ask, what the dimension. That's just because that just comes from the fact that every phi has dimension n. Okay, every time you have some derivative that's like 1 over distance, so you get some dimension that's n plus n. Okay. So you can then ask, how this will contribute to some processes of some energy, and just by dimensional analysis, the contribution of this looks like gi to some power lambda I to the power, to energy E. Okay. So this is just from dimensional analysis. You can ask what is the contribution that you'll get, and the contribution will be this way. Okay. So if delta I is large, then this coupling constant will contribute more at higher energies, and if delta I is small, then this coupling constant will contribute less at low energies. Okay. So there's some part of this answer which is just fixed by dimensional analysis. Okay. Now you can ask, instead of writing down this kind of a coupling constant, it makes sense to ask about the value of some dimensionless coupling constant. Okay. The dimensionless coupling constant, since we are now taking the idea of a cutoff lambda seriously, okay, you would naturally have said is, you'd write gi as lambda I, okay, to the lambda to the delta I minus 4. And then you see, if you ask how it contributes to some process of some energy E, then what you get is EI by this lambda, okay, to the power delta I minus 4. And then what appears in front of it is just some dimensionless coupling constant. Okay. So if you want to ask about the importance of G, okay, at some energy, then there's some part of it that's just fixed by this. And then you want to ask, how do these dimensionless parameters scale? Okay. Because those are things which will. So, for instance, let's say you want to ask what happens at low energies. Okay. The one way you would do this is, let's say you had some cutoff which was at some very microscopic scale. You try and flow the cutoff down to some energy scale that you wanted to work in. Then let's say, you had some energy processes of some energy EI, which were of the same order as the cutoff lambda, or, maybe 10 times smaller than the cutoff lambda. Then, you do some calculations, you'd get some factors of EI by lambda to the delta I minus 4. And then you could ask what about the dimensionless coupling constant that appears in front of it. Okay. Okay. So, you can now ask, what happens if you start changing this cutoff. By the way, this process of changing the cutoff you can formalize, okay? And you will sometimes see it written in this way. You can imagine. In fact, let me give you a reference if you want to see this discussion. There's a reference here somewhere. Yeah. You can try looking at this is by Pulczynski. Which is a review of some of this perspective on, how renormalization group works. Okay. So you can try and ask, that question, and as I said, some of the answer is just fixed by dimensional analysis. And one way to formalize that question, how do these GIs change as you flow the cutoff lambda? This is some dimensional analysis, but you can also ask the question the following way. You can imagine that you're doing some path integral, which we haven't, which we haven't discussed. But you can imagine that you're doing some path integral, and there's some path integral which depends on the cutoff. So right now we haven't discussed the path integral for field theory. Okay? But let me just say that there is some process where you integrate over fields, okay? And you can compute all correlation functions by computing some path integrals with some action, okay? And some insertions of some field operator. So say you're trying to compute some physical process, the expectation value of some operator A, then what you would do is you'd have to compute some path integral where you integrate over these fields phi. Then this process of flowing the cutoff from, so in this integral, what you do is you say that I will only integrate over modes that are below lambda. So you can make this well defined. By cutting off the measure so that d phi only has modes with energy smaller than lambda. Okay. And as I said, by the way, it's pretty important that when you do this, you should do this really in Euclidean space. Okay, if you really wanted to do this, you should first rotate. That's why I wrote e to the minus s lambda. You should first rotate to Euclidean space and then ask about some correlation function. And in this, you say that you cut off this measure. Now you can say, let me now do part of the path integral. Okay. Now do the integral over modes between lambda and lambda prime. So you can't flow out, but you can always flow in. Okay, if you're given the UV theory, you can't say what happens if you make the lattice scale even smaller, but you can ask what happens if you make the lattice scale bigger. So you can ask, here's some integral, I'm doing some integral, and this d phi is really an integral over different modes when you write this kind of a functional integral measure. Remember, this d phi you could write as product over I d phi I, where this is some basis that you use to describe the field, and this basis you could take to be in some momentum space basis. So you're really literally doing some integral over modes, okay, of different energies. And then you could say, you know, let's do the integral over modes between lambda and lambda prime. If you do that integral, then you know you will get a different integral. Okay? So this is equal to e to the minus s lambda prime. Say you're measuring some operator A which which doesn't itself care about the cutoff or doesn't care about these high energy modes. A, and with this different measure, let me call it d phi prime. Okay. And this tells you, so by doing this integral, you can really say how the action changes as a function of the cutoff lambda. Okay. And that's the same as asking this question of, how do the GIs change as you flow the cutoff lambda? If you wanted to ask this question the full quantum theory, then this is how you would ask it. You define this path integral and you literally do the path integral over some shells. And once you do the path integral, you're left with a different action, which has now a different cutoff, but gives you the same physical answers. Okay. Okay. So this is the kind of question that we want to ask. Of course, in perturbation theory, we don't try to do the full path integral, but we try and ask just by doing some one loop calculations or two loop calculations, how these parameters change. Okay. Yeah.
The action is already defined.
The action is defined in terms of the cutoff, correct.
So
now I change the measure. Now I do some of the path integral. When I do the path integral, this action has modes of this energy lambda and some other modes of energy lambda prime. Once I do the integral over the high energy modes, I will be left with some action in terms of the low energy modes, which will be a different action. It won't be the same action. That's right. So you do the integral. Literally do the integral. Okay. That's what integrating out is.
That gives you the action.
It gives you a new action.
And if I directly define my action in terms of the lower cutoff?
Well, I mean, so the point is this action with, this action gives you the same physical answers as this action if you ask questions about low energy observables. Of course, you can, you could have defined the same action, but the question is, let's say I give you some action at high energies. What is the action at low energies that gives you, what is the action at a slightly lower scale that gives you the same answers as the original action gave you? Okay. So you see, if this process defines for you some flow in the space of GIs as a function of the cutoff. Okay. That flow is the RG flow. So is this not clear or is? Huh? Well, you can go as low as you like. Basically, at some point, there's some physical question you want to ask, which is determined by what operator you put in there, right? If that operator, so as long as your cutoff is higher than, so we're asking questions about some operator at some energies. You can flow the cutoff as long as, if you try to flow the cutoff below that, then of course it won't make sense, right? But as long as your cutoff is, not is above the level of whatever scale you want to ask questions, you can flow the cutoff down, right? Yeah.
Not related. If I want to calculate the final propagator after 1 loop, can I find it from here?
Can you find what from here?
The Green's function.
Can you find what from here? Sorry, I didn't understand. Huh.
2.2.
Huh.
Can I find it directly from here? If I give you A, B, C, D values,
huh.
Can you directly tell me the answer?
What do you mean if you give me A, B, C, D values?
Like we have to find A, B, C, and that we find by doing one loop calculation and making it finite.
Correct.
So if I give you A, B, C values,
If you just tell me what ABC are, then the propagator is just the inverse of the quadratic part. Yeah.
I can relate where propagated to this by this coefficient. The given endpoint green function.
Yeah.
If I just write field phi goes to a phi, like that, can I relate these two?
I'm not understanding. What's the question? Maybe I'm jet lagged. Yeah.
Like tau of x1 till xn.
Yes.
With mass m and g coupling.
Yes.
Now can I relate this bare coupling, bare propagator to counter term propagator by rearranging, rescaling phi and g?
Bare propagator to counter term propagator. Sorry, I'm sorry, I'm just really not. No, just explain the question. Maybe others also have. What do you mean by bare propagator to count? What do you mean by counter term propagator?
No, tau of x1 till xn with mass m and g. And can I relate with tau of x1 till xn with mass zmm and zg?
What is z and what is zmm?
Scaling of mass and coefficient.
Where did I write z?
I write m going to zmm.
Oh, if you write m as a different z, I mean, you will have some answer in terms of, so one second, are you asking about the physical parameters?
Yeah, physical.
So, then I'm not understanding. Then you have the answer. When you do some calculation, you will get some answer. It will depend on some physical parameters. You're not doing it, you're not doing it for m equal to 3 kg, right? You're doing it for m equal to m. So what is the, I'm not understanding. It's not like when we do perturbative calculations, we get an answer which is a function of m and g. That by itself says, if I give you a different, it tells you what the function is, a function of m and g, right? We don't do it for like a specific thing like m equal to 1 GV.
Tau of, let us assume I have a propagator in terms of m and g, mass endpoint green function. Now, how will I calculate after for one loop without doing this?
What do you mean without doing this?
He's asking if we have some quantity, say 4-point function in
Yes.
Before doing these adding counter terms.
Okay.
So we have one quantity in terms of m and lambda. Now I added counter term, so I will get another expression for m and lambda in terms of this new quantity. Like
oh, good. So,
so then from the earlier result, can we write that?
Oh, okay. So I see. So this is something we did right earlier. So first of all, I'm not understanding the relevance to what I'm saying here, but it's some question about the earlier procedure. But indeed, it does work like that. But in the following way, this is a question about some slightly different issue, but let me answer it in any way. For instance, in this case where we took the idea of the cutoff seriously, what we found in the phi to the 4 theory, for instance, was that if you looked at this kind of a process, right, then this looked like, there was some term here. Let me forget about the i's and so on. So let's say you computed the IM K1, K2 to K3, K4. And this had some term which looked like minus I lambda plus lambda squared into something which looked like log of lambda by S. Right? So this is what it looked like in terms of these terms. Yeah. And then we said, well, there's a dependence on lambda here. So we said, well, indeed you could have written this also in terms of A. So there's another contribution which is minus IA. Right? And there will also be, of course, plus IA squared. Like in principle, you can replace lambda with lambda plus A and you would get the same calculation. But then we said, well, let's set A equal to log lambda. If you do that, then you will get some finite answer, which will just be in terms of S. That's what we did. So of course, if I give you the answer as a function of lambda, the answer as a function of lambda plus A is the same thing with lambda replaced by lambda plus A. It has to be. But these two things go at different orders in perturbation theory. Because A goes like lambda squared, replacing lambda with lambda plus lambda squared means that the first order term doesn't get changed, but the second order term does get changed, and that's how we were doing things in perturbation theory. Yeah? But this is not relevant to what we are saying right now, right? Or is it relevant in some way? Okay. What I'm trying to ask here is, something slightly different if I'm being too abstract. This is some physical thing. Let's now take the parameter seriously. Okay. So we get some physical amplitude which looks like this. Okay. Now we are trying to ask, let's say I changed the value. So this is, imagine that you were not doing, this kind of perturbation theory where you separated parameters into bare and physical. Let's say you just had some parameters which look like lambda, and you also took seriously the capital lambda cutoff. Then you do a calculation, you would find this answer. Then you could ask, as I change my cutoff lambda, this cutoff lambda, how does small lambda change? And that's the kind of question that we're asking. And you can answer this kind of question, the full quantum theory, by doing this. This is not what we actually do ever in practice, but this is one way to think about how you're answering these questions. It's one way to think about how we're answering these questions, because you might have thought, what if I did a one loop calculation for 2 to 2 scattering to see how this lambda changed? And then I did a one loop calculation for 3 to 3 scattering. Why does it have to change in the same way? Okay. And what this tells you is that it has to change in the same way because what you're doing is something physical. You're really integrating out some modes. Okay. So it's not just that what you're doing is specific to one particular calculation, but rather that you're integrating out some modes. Okay. So this kind of a question you can now so you can ask how these parameters change. So that's the question that we asked about here. How do these GIs change as you change the lambda? And now I'm making it precise here, in that you do this path integral. This S lambda here looks like those GIs, but all those GIs are functions of lambda. Okay? And then you can ask, how do they change as functions of lambda? Okay, okay, good. Now the point is that there are some things you can just make. So often the way this thing is written is in this form. Just to make everything dimensionless, okay, we often write things in this form. Okay, so remember, G has some dimension which looks like delta I minus 4. Okay, therefore, just to make dimensions match, you write things in this way. And this function that appears on the right hand side is called the beta function. In principle, it depends on all the GIs. Now you see, just by dimensional analysis, in terms of this lambda, which is we can write delta I minus D lambda I plus beta I lambda I. This is just, I didn't do anything here. I just replaced this in terms of these dimensionless parameters here. Okay. You see now what this tells you already. Did I get this? Yeah. What this tells you already is that, let's say you look at some lambdas which have delta which is larger than D. Okay. That means that lambda D of small lambda by D of capital lambda, the leading term, so this term you expect is something which is perturbative. Okay. It depends on the various other lambdas, okay. But it probably doesn't have any order 1 contribution. Okay. So this is some term which depends on the various lambdas but doesn't have any order 1 contribution. But here you see a leading term which does have an order 1 contribution, and you see that in the case where you have delta I larger than D, you will get some terms which damp the flow as you flow down in energy. So for instance, if delta I minus D is equal to n is greater than 0, then what you will get will be lambda D lambda by D lambda is equal to n lambda I plus some other beta I lambda I. And in the limit where this is small, you see as you go down in energy, the flow is just dominated by this. And this looks like a positive eigenvalue, but it's a positive eigenvalue as you raise the cutoff. As you lower the cutoff, it's a negative eigenvalue. Okay. So you see that what this tells you is that, and which is kind of clear, is that the answer to the question above is simply that okay, the answer to this is, as I said, some of the answer is just determined by dimensional analysis. And the answer is that is damped as we lower the energy. Okay. Okay. So this part of the answer you can just get by dimensional analysis, and the flow of relevant parameters grow in size as we lower the cutoff. Actually, I should say cutoff. Okay. And marginal parameters you can't answer by dimensional analysis. Okay, you have to do a more complicated calculation. Yeah. Okay. Now, so what this tells you in particular is that if you have some parameters which are irrelevant at high energies, then as you flow the cutoff down, these parameters basically just get set to 0. They don't contribute much at lower energies. Okay. Therefore, what remains at low energies are only marginal and relevant parameters. Okay. Therefore, at low cutoffs, we always see effective field theories with only marginal and relevant parameters. Okay. And this is just some statement that comes from dimensional analysis and thinking of things this way. Okay. Now, this statement, maybe you people have also heard discussion of the renormalization group in other contexts and so on. So it might seem like an obvious statement, but I want to emphasize this was actually a pretty surprising, a pretty deep understanding when it came about, for the following reason. You see, people were playing around with quantum field theories all the time, even in particle physics, right? And we had the standard model. And then we had all this discussion of renormalizability and these tricks and when we can get rid of things. And someone could have said, why did it happen that the standard model is a renormalizable theory? Why is the standard model renormalizable? Why is nature being kind to us? Or some of you know the answer. It's written on the board, but why is it renormalizable? Well, yeah, it's the fact that it's a all low energy effective field theories can have to be renormalizable because you only will see relevant and marginal parameters. Okay? So it's not that nature is kind to us. It's that if you ask low energy questions or you ask sufficiently low energy questions, then you will necessarily see only these relevant and marginal parameters, which is precisely what we are calling, So all this, the fact that the standard model is renormalizable is only telling us that we are asking questions at some energies that are small compared to the cutoff. Okay. If you were to start asking questions at energies which are close to the cutoff of the standard model, then you would find that you would get terms which look like non-renormalizable terms, like these irrelevant terms. But maybe if you then found some more physics, or you found a different description of the theory that was at a higher cutoff, then those terms you could also write in terms of renormalizable terms. Okay. So indeed, when people first looked at weak interactions and so on, they did write down various non-renormalizable effective field theories. And then in the standard model, it was all made renormalizable because we just found a description of the theory so that we are asking questions that are well below the cutoff. So it's not that nature is kind to us and we're lucky that we saw a renormalizable theory as opposed to a non-renormalizable theory. If you formulate the physics correctly and you ask questions below the cutoff, quantum field theories are always renormalizable just because of this reason. Okay. Okay. Okay, so this is, of course, there's the issue of what happens to marginal parameters, and that we discussed last time about the phi to the 4 theory. Okay, let me also say one more thing. you might have thought that the fact that the flow of irrelevant, and this is something which people often get confused about, you might have thought the fact that the flow of the irrelevant parameters is damped as we lower the cutoff means that the irrelevant parameters don't matter at all. In that, I have some high energy theory. I put some irrelevant parameters, maybe 5 to the 6, 5 to the 10 or whatever. Then I flow the cutoff to a low energy scale, and what values of the parameters I put don't matter at all. But this is in fact not correct. The reason this is not correct is that, and actually this paper by Pulczynski kind of explains this nicely. The reason this is not correct is because so irrelevant parameters are not complete, irrelevant parameters can alter the flow. Okay. The flow of other parameters. Okay. So the statement is that if you take a theory, okay, with a, so consider S lambda, okay, with some irrelevant parameters. Let me call them lambda IR, and some marginal and relevant parameters. So imagine that you have this S lambda. Earlier I was writing in terms of sum of GI, but now let's say, or sum of OI, but let's separate this, okay, into some parameters which are irrelevant and some parameters which are relevant. At low energies, and this is the important point, same predictions as S prime lambda, okay, but where lambda IR has been set to 0, okay, but this lambda marginal and lambda some lambda prime marginal and lambda R has gone to some lambda prime R, okay. So, let me just say this in words. I don't know if my notation was great. Let's say you think of some theory at a cutoff which is very high, and it has some irrelevant parameters lambda R, lambda M, and some lambda IR, and some marginal and relevant parameters lambda M and lambda R. Okay. Then you might have thought if you lower the cutoff or if you ask low energy questions, then these irrelevant parameters never matter. But that is not correct. Okay. If you lower the cutoff, if you want to ask questions at low energies, then the correct statement that you get from here is that this has the same physical predictions as a different action where you set the irrelevant parameters to 0, but where you have modified the values of the marginal and the relevant parameters to something else, not the original values. And this something else can depend on what these values were originally. Okay, is it clear what I'm saying here? And this is in fact how one way to understand what we do when we do renormalization. Okay, we say that we have some marginal, so we could have had some 5 to the 6, 5 to the 8 and so on, but we can always find a description where those terms simply don't exist. And the physics at low energies, you can set those terms to 0, provided you modify also these terms in a way that you get the same physics at low energies. Okay, is this clear what I just said right now? Okay, so that's something to keep in mind, that it's not that the irrelevant parameters are simply irrelevant, it's rather that their low energy predictions can be captured by another theory where they don't exist, okay, where you set them to 0, provided you modify the relevant and the marginal parameters. Yeah. Why what? Yeah, it's because of this. It's because of the fact that, let's say you start with some lambda I which is order 1. Okay? Then you write down some coupling. This is discussed a little bit in this paper. Let's say, so what you'll get is you'll get some coupled set of differential equations. It's true that as you go to very low energies, lambda I or let's say you think the example discussed here is I think the 5 to the 4 plus 5 to the 6 theory. As you go to very low energies, lambda 6 or low cutoffs, lambda 6 will go to 0. But lambda 6 was not always 0. At the high cutoff, it was 1. At that point, it could have changed the flow of lambda 4. So lambda 4 that you get at low energies might not be the same as what you would have got if lambda 6 had always been 0. On the other hand, now at low energies, lambda 6 is 0. So you could have set lambda 6 to 0 in the first place, provided you started with a different value of lambda 4 in the high energy theory. Is it clear what I said? So this is something which is important to understand. It's not that the cutoff scale, if you get irrelevant parameters, always important. Rather, you can find a different theory where you get the same answers. Okay? And when we say same predictions, these same predictions means up to, one, I'm going to write 1 over lambda, but what that really means is, if you're making predictions at energy E, then up to energy E over lambda. Okay. So it's not, of course, that all predictions are the same, but predictions are the same up to energy E over lambda. For instance, you could have said, the gravitational interaction is an irrelevant parameter, right? So, we see that in the standard model. However, it's also true that at low energies, the gravitational interaction doesn't matter. So if you thought of a different theory in which you just set gravity to 0, that in fact does give you the same answers at low energies as this does. And that indeed, that's the reason why it's so hard to measure consequences of gravity, because and particle physics experiments or the kinds of energies we can usually access, the implications of gravity are small precisely because they're small at low energies. Okay. So that's what I wanted to say about this. Of course, we can then ask about the marginal parameters, and the flow of the marginal parameters is interesting. Let me remind you once again of this beta function discussion. Yeah.
What we are trying to do in the board, how GI flows.
Yes.
As we lower the cutoff lambda.
Yes.
Constraint to that, the expectation value of the observable.
Yes. No. I didn't say that. Here there's not constraint to anything. Here we are just trying to compute an expectation value A. You see, what we did earlier was slightly different. We said we compute some 4-point function, and then we ask, this 4-point function is some physical function, and that was the discussion we had when we said the counter terms. That's not what we are saying here. Here we are saying we're just doing the path integral with some action with some cutoff lambda. Now you can do this. You can just do part of the path integral. A is what it is. A doesn't involve the high energy modes. The whole action reduces to this action below. I mean, the expectation of A in the end is obviously going to be the same because you just did part of the integral.
You're setting the
this, that's just, we are just doing some integrals. What we are doing is pretty simple. It's like saying, let's say I had this integral minus xy minus y squared. Okay, and I was trying to compute x cubed. Say I was trying to do this integral. Okay, I could just first do so this is some action. I could do the integral over y. If I did the integral over y, what would you get? E to the minus x squared. What happens when you do the integral over y? You get what? Square root of e to the minus x squared by 4. One more. Is this correct? I think you get another minus x squared by 4, right? Because you complete the square, you put a minus twice xy, and you put a minus of x squared. What do you get? It's not plus, right? Is it plus or minus? Plus x squared, right? Okay, let's complete the square. Minus x squared. Yeah, I just want to do the integral of y, so I write this is minus twice xy minus xy by half. 1 second now since I'm jet lagged, and so I write this is minus x squared by 4 And this I could write as, I could have taken this off and written this is minus 3 by 4x. Yes, you get a plus. Okay, so anyway, you get a plus, okay. So let's say I do this integral, okay. So doing this integral is the same as doing the integral with e to the minus 3 by 4x squared, right, x cubed. This action is the same as this action, but I had to change this parameter from being 1 to being 3 by 4.
And you can do this because A doesn't depend on the...
Because A doesn't depend on Y, but you see A, that's right, A doesn't depend on the high energy modes. A is a low energy observable. Any question you ask about low energy observables, if you had 10 other variables here and A didn't depend on Y, A could depend on all those variables. So there's some low energy variables, some high energy variables. You do the integral of the high energy variables, you're left with a different action. It's not the same action as the original action you had, okay? But it still gives the same answer for every function of x that you want to compute. But you have to change the parameters, okay? Of course, in quantum field theory, the actions are much more complicated, but it's exactly the same process in principle.
A doesn't depend on high. How do you... So observable can be represented as a product.
Correct.
How do you exactly make sure that it doesn't...
Any long distance observable doesn't depend on high energy modes, right? You want to ask a question about a physical observable.
Okay, so you have to look at it in the Fourier space and see.
Yeah, so you know these are conceptual things. You can ask a question about an S matrix if you like, which doesn't depend on what's happening at high energies. That's also some correlation function, which we'll see. So you can ask questions, yeah, but or you can look at it in Fourier space. You can ask a question about correlation function. But any low energy question that you ask will not care about what you're doing there. Yeah, so you want to ask a question, you can ask a question about, you can do this in position space. You can ask a question about, I don't know, correlation at distances which are very large compared to this. And that observable is largely insensitive to what you do with lambda.
The action is changing in such a way that quantity...
Yeah, but we are not using that as a criteria to calculate the new action. It's not that I said the expectation value of x cube shouldn't change, therefore I got the 3 by 4. I got the 3 by 4 by doing the integral over y. In this case, yes, but let's say I had many more parameters. I had like z cubed and so on, and I had this x y coupled to all of them, right? Maybe there was a y z by 2 or whatever, right? Then just by setting the value of x cubed, I couldn't see what the new action is.
Writing your theory now in terms of lambda prime automatically
means all physical values have to be the same, right? But it's true that if you computed enough physical values, you can guess the parameters of the new theory. That's how we often work in perturbation theory. But really the correct way is you do the integral. Okay. Okay. Well, in the case of gravity, well, what we don't know what the gravitational coupling constant is doing at what some high energy scale. So for us, the answer here is we can work with an effective action where the gravitational coupling is just set to 0, and that's because gravity has a very small effect on us. Okay. So we can work with some effective action. Now you could say, well, we could work with a different effective action where it's not set to 0 and where the standard model parameters have different answers. But that's not relevant for us, right? We can work the simplest effective action we can work with is where it's just set to 0. That's what we do here. By the way, even in the question of renormalization, if you wanted, you could have made your life very difficult by saying, let me add 5 to the 6 counter terms and 5 to the 8 counter terms and let me compute things, and you could have. And you would have still got the same answers that you get at low energies. Do you see what I'm saying? You could have said, let me add a counter term for 5 to the 6. And then that counter term would have given rise to other counter terms. But in the end, the physical answers you would have got are the same. So what we do in renormalization usually is we say, at low energies, we'll just set all those 5 to the 6 and 5 to the 8 and other parameters to 0 in the UV scale. And it's justified to do this because, because of the way just dimensional analysis tells you that, whatever you set them to be, they shouldn't have an effect at low energies. Is this clear or? Okay, let me just remind you of the discussion we had about, oh man, I wanted to do much more today. I don't know how we went so slowly, but okay. Let me just remind you a little bit of, how the beta function discussion we had last time in this language. You can compute these beta functions pretty effectively just by keeping the cutoff. Okay. As I said, let me write it here. In fact, maybe the simplest way to compute the beta function, in fact, is not to look at the full renormalized perturbation theory, which of course we can do, but just keep the answer with the cutoff. So let me remind you the answer that we got, right? Yeah, let's look at for marginal couplings, we have to compute the beta function. So marginal couplings also change the same way that relevant and other irrelevant and other couplings change. Marginal couplings also change. It's not like they don't change, but you have to calculate how they change, right? So in particular, let me remind you how we did this calculation already, but let me just repeat it just to refresh your memory. Remember, we computed this scattering amplitude in the 5⁴ theory, which went like this. Okay, there was various notation we had for these AIs. They involved s into x minus x squared minus m squared. You'll find it in your notes. Okay, but in fact, for the purpose of computing the beta function, none of this is important. All that's important is this term, which is the dependence on the cutoff, and the fact that there's a 3. Okay. And then there are some other terms which look like minus 3i lambda squared by 32 pi squared plus some order 1 over lambda squared. The only term that's important for computing the dependence on the cutoff is this, okay, and this. So in fact, all these terms that we spent a lot of time trying to compute with great difficulty, which tell you how the dependence on the s and the x's and so on is, are not important for computing the beta function. You only need this dependence on the cutoff in this term here. Okay, and so if you do that, then it's important actually to get the sign right. So you will find that if you so you now want to ask that this physical answer should stay constant as a function of lambda. Okay. That's what I said. What we should, as I said, what we should really do is integrate out the full action. But in this case, there's only one parameter we are keeping track of, which is lambda. Therefore, if you just demand that one quantity should stay constant, which is what we are doing here, you can guess how that parameter changes. As I said, that's not the thing you should do in general. You might have more parameters, and you might have to do write down beta functions for other things as well. But here there's only one parameter. That's the only thing you want to see. So instead of doing this whole procedure, you can now demand that you just demand that this amplitude stays the same as you change the cutoff. Then you can ask how this lambda changes as you change the cutoff. Okay. So we said dm by d lambda equal to 0. Okay. And that just sets, you just have to set this, and that tells you that minus lambda, I hope, plus 3 lambda squared by 16 pi squared is 0. Okay, this becomes 16 pi squared because there's a log of lambda there. Okay. And that's it. And then you could just solve this after this. Okay. And we already solved this, I think, last time. And the answer is that you'll find that lambda 2 is lambda 1 by 1 minus 3 lambda by 16 pi squared log of capital lambda 2 by lambda 1. Okay, so if you flow lambda from lambda 1 to lambda 2, then you have to change small lambda in this way. Okay. This is an example of how you explicitly have to change, this is lambda 1, how you can compute the flow of marginal parameters as well. Okay. In particular, what you can see here is that if you start with the theory at some value of the cutoff, okay, and you try to ask, let's say you try to flow up, you try to ask what happens as you go to higher and higher values of the cutoff. At some point, you would hit a pole. Okay, the theory would become very strongly coupled, and that's, you can see from here. Whenever this term becomes 0, okay, you see that what will happen is lambda 2 will go to infinity. Okay. That is called the Landau pole of the 5⁴ theory. It tells you in particular that if you start with some effective field theory with some value of the cutoff, and you really wanted to take a continuum limit where you wanted to take the cutoff scale to infinity or the cutoff scale in position space to 0, then you couldn't do that because before that you would hit some strong coupling. Now that's what this kind of one loop analysis tells you. I think last time we discussed what happens. How do you know that the flow doesn't somehow get damped in non-perturbative regime? You don't know, but at least perturbatively, it looks like you wouldn't be able to take that limit. Okay. And famously, for the case of gauge theories, this coupling becomes weaker as we go to high energies, and therefore, for those theories, you can take a limit, a continuum limit. Okay. So sometimes you can take a UV, so taking this continuum limit is called UV completing the theory. And the reason it's called UV completing the theory is because you're making some guess for what the ultraviolet physics is or what the very high energy physics is, even if that is not what is really happening in the world. Okay. So when we say that gauge theories are UV complete, it doesn't mean that the world to arbitrarily high energies is described by QCD. It just means you can make a guess by saying that the world to arbitrarily high energies is described as QCD, and that's a theory that's mathematically complete. It's a UV completion of QCD, and at low energies it will give you some predictions, and that's so when we say we UV complete a theory, it doesn't mean, as I said, that physically the theory is correct all the way in the UV, but just that in principle you can UV complete it. The 5 to the 4 theory, for instance, is not UV complete by itself. Okay. Okay, so that's what I wanted to say about these beta functions and this issue of RG coupling. I think we said some of this before, but I just wanted to say it once again after we had discussed all this, had this discussion of renormalization. I wanted to start a discussion of path integrals today, but this might not be a good time to start since I said we'll finish by 5:15. Are there any questions about this? So there's some assignment which was sent out, which is due next week. So try and do that assignment. Okay. That's right. That's right. When you say that QCD is UV complete, it has, we are taking a right. So in this case, in the case of QCD, what happens is this coupling constant has the opposite sign. Instead of 1 minus, you get a 1 plus. Okay. So here, instead of getting a minus sign, you'll get a plus sign. Okay. Or in this case, you have a plus sign, you'll get a minus sign here. Okay. If you have that, then this coupling has a property that it becomes weaker at high energies. Okay. Now, that means that in principle, you could take, let's say this had the opposite sign. In principle, you could take this cutoff lambda 2 to infinity. And what would happen is this small lambda 2 would become smaller and smaller. It would go to 0. So you could say, well, here is a theory which is defined all the way up to infinite cutoff. Okay. But that doesn't mean that physically the world is described by that theory all the way up to infinite cutoff. Just that, it makes sense to think of a model of this theory at arbitrarily small cutoff, arbitrarily small lattice scale, and that model is physically consistent. Is mathematically consistent. Is mathematically consistent, even though it might not be the correct description of the world at very short scales. Yes, if it becomes constant, then also you can do this. That's called a non-trivial fixed point. So you can have such fixed points where what happens is that as you flow, the coupling constant doesn't go to 0, which is what is happening here, but in fact it goes to some non-trivial fixed point. That can also happen. It happens in various cases. That kind of fixed point also exists. So it's not necessary. Indeed, it's not necessary that the coupling constant has to go to 0. It could go to some other non-trivial fixed point. Such non-trivial fixed points are rare. It's not easy to find them, and they rely on at least in 4 dimensions. It's not so easy to find them, and you often need various other symmetries to be able to find these examples. But in principle, yes, you could find these things. Yeah. In 3 dimensions, it's easier to find such non-trivial fixed points. In 2 dimensions, it's quite easy to find. That's non-trivial fixed points. Why does it depend on dimension? This is why is it easier to find conformal field theories, non-trivial fixed points in 3 dimensions and 2 dimensions? It is it is easier, but I don't know if there is if there is a very satisfactory answer to that. It just is easier. It is the case that we know of lots of examples of fixed points in lower dimensions, and finding fixed points in 4 dimensions seems to require various symmetries, and I don't know of any very good example that tells you that in 4 dimensions you can't have more complicated fixed points. It's kind of what our knowledge of quantum field theory is. Maybe there's a better answer, but I don't know what the better answer is. I think it's kind of a reflection of what our knowledge of quantum field theory is. It could be that tomorrow we'll go and find a huge number of fixed points in 4 dimensions for other quantum field theories. Although it's probably not, and it's just is the case that it's much easier to find. It has to do I don't know if there's a very satisfactory answer to that question. Why it is that it's easier to find fixed points in lower dimensions than in higher dimensions, but it is. It's true that it is. At least this is as I said, this is a question of our current knowledge. It's not a mathematical theorem that you don't have fixed points in high dimensions. You could have, and maybe tomorrow we'll find a class of all sorts of. It would be very interesting if we were to, although probably unlikely. Okay, sorry, I wanted to say a little bit more, but let me stop here. And maybe next time we'll start discussing path integrals. Are there any other questions about this or about renormalization? Since you have a few minutes, we can discuss them if there are any other questions, or if. Okay, so Wednesday we'll meet at the usual time, which is, yeah, so we'll just